Hello everyone, I'm Hanzhi Wang from Renmin University of China. It's my pleasure to present our paper here. This paper considers the problem of estimating a single node's PageRank on undirected graphs. We successfully tightened the query times upper bound of this problem to the minimum of dt and the square root of m. Here dt denotes the degree of the target node t, and m denotes the number of edges in the graph. This work was completed under the supervision of my advisor, Professor Zhe Weiwei from Renmin University of China. Next, I will show the details of this work. First, I would like to briefly introduce the definition of PageRank. PageRank is actually a very famous, popular, influential, and widely adopted metric for evaluating node centrality on graphs. It was first proposed by the co-founders of Google in 1998 to calculate the global importance of web pages in Google's search engine. It is defined based on the intuition that a web page is important if this page is linked by many other web pages, or this page is linked by some very important pages. For example, in the toy network, we believe the page U is an important web page on which the information was trusted if page U is linked by many other pages, or page U is linked by some known to be important web pages, like page V. Such intuition can be formulated as a definition formula if we convert the real-world network structure to a graph. We note that the definition formula of PageRank is presented as an iterative equation, where the pi vector is called the PageRank vector, whose use entry pi u records the PageRank score of node u, and the matrix P denotes the transition matrix of the graph, where P inherently equals the adjacency matrix A times the inverse of the degree matrix D on undirected graphs. On the other hand, for any node T in the graph, its PageRank score exactly equals the probability that an alpha random walk generated from a random source node in the graph terminates at node T. Here, the alpha random walk refers to a specific random walk simulation process that at each step, the walk either terminates with probability alpha or moves to a randomly selected neighbor with probability 1 minus alpha. Here, alpha is a decimal between 0 and 1. We consider alpha as a constant throughout the paper. Above is a brief introduction to the definition of PageRank. PageRank was first proposed in 1998 and has become one of the most influential metrics on graphs over the last decade due to its simplicity, uniqueness, generality, guaranteed existence, and of course, the success that Google achieved. Its application has been far beyond the original web search, covering information retrieval, recommender systems, social networks, even biology, chemistry, neuroscience, and so on. In this paper, we focus on the problem of estimating a single node's PageRank on undirected graphs. Specifically, given an undirected graph G and a target node T, we aim to estimate the target node T's PageRank score within constant relative error and constant success probability. Note that the output of this problem is only one decimal, that is, the estimated value of node T's PageRank. Thus, we believe a humble goal of this problem is designing a local algorithm whose query time complexity can be sublinear to the number of nodes n. In other words, since we are only interested in the target node T's PageRank, we hope the query algorithms for this problem is a local algorithms, which only needs to explore a small fraction of the graph. However, even for this humble goal, existing methods can seldom achieve it. For example, the first 4 algorithms listed in this table fail to achieve a sublinear query time complexity in terms of the number of nodes n. The fast PPR method and the bi-PPR method provide the upper bound for this problem before our paper, which can achieve the complexity of the square root of n times dt. In comparison, in this paper, we propose a novel method setpush, which tightens the upper bound to the minimum of dt and the square root of m. To see the theoretical improvement of our setpush, recall that the upper bound before this paper is the square root of n times dt. Since dt is always smaller than the number of nodes n, our complexity bound is always better than the previous bound. In particular, for a tiny dt, the improvement of dt over the square root of n times dt is significant. On the other hand, when dt is large, for example, when dt is larger than the average node degree d, the square root of m may dominate our complexity bound, where m is the number of edges in the graph and m equals n times d. Thus, for a large dt, especially when dt is larger than the average degree d, the larger dt is, the more significant improvement achieved by our stat push is. In the following, I will illustrate the limitations of existing methods and explain the reasons why our stat push can achieve a better complexity bound. First, let's see the limitation of the canonical Monte Carlo method. Recall that the PageRank score of the target node T equals the probability that an alpha random walk generated from a random source node terminates at node T. By this interpretation, the Monte Carlo method generates multiple alpha random walks on the graph. Each random walk is generated from a random source node. Then the Monte Carlo method uses the fraction that the number of alpha random walks terminates at node T over the total number of random walks generated in the graph as an estimated value of node T's PageRank. Such Monte Carlo method is cut out to estimate large PageRank scores. However, for small PageRank score, like pi t equals 1 over n, if we want to derive an estimator of pi t within constant relative error, the Monte Carlo method needs to generate no less than n walks to ensure that node t is touched by random walks at least once. Therefore, in the worst-case scenario, the random walk complexity of the Monte Carlo method cannot be sublinear to n. This slide presents a toy example for such worst-case scenario. If we are given node V as the target node for single-node PageRank query, the Monte Carlo method has to cost O(n) time to estimate pi V. Another line of research estimates pi t by reversely pushing the probability mass from the target node T to its ancestors. More specifically, this line of research maintains a variable RUT for each node U in the graph, which records the probability mass that has been transferred from the target node T to the node U reversely. In particular, RIUT records the probability mass transferred from T to U at the S push step. Initially, these push methods set R0TT as 1, referring to that we put 1 unit of probability mass at node T initially. Then during the push process, each node U with non-zero RUT transfers its probability mass to its neighbors according to the transition probability. Finally, we return the average of RIUT over all nodes U and all steps I as the estimator of pi t. The push method is cut out to estimate small pi t since we reversely push the probability mass from T to its ancestors. However, a hard instance for this push method is to push probability mass from a large degree node. For example, as shown in the toy graph, when we are given node U as the target node for the single node PageRank query, the push method costs O(n) time even after the first push step because the degree of node U is n. As a result, this push method still cannot achieve a sublinear query time complexity for an arbitrary target node in the worst-case scenario. Recently, a set of works proposed to combine the Monte Carlo method and the push method in an effective way. The rationale behind this hybrid method is that the Monte Carlo method and the push method have complementary advantages. The Monte Carlo method generates forward random walks in the graph, which performs well when pi t is large. The push method reversely pushes probability mass from the target node T, which can efficiently estimate small pi t. However, these methods can only relieve the limitations of Monte Carlo and the push methods. In the worst-case scenario, the push operation still costs O(n) time right after the first push step, leading to inefficient query cost. In addition, recall that this paper focuses on the single-node PageRank query on undirected graphs, and the upper bound before our paper is the square root of n times dt. In comparison, for the problem of estimating a single node PageRank on directed graphs, a proved lower bound is given here, where delta denotes the maximum node degree in the graph. We note that the lower bound on directed graphs is even larger than the upper bound on undirected graphs. This is because there are some nice probability of PageRank held only on undirected graphs. However, most of existing methods fail to well utilize this probability, resulting in inefficient query complexity. Next, I will present the details of our set push algorithms and explain the superiority of our set push over existing methods. As an overview of our set push algorithms, we follow the push structure adopted in existing push methods to push probability mass from the target node T step by step. However, a major difference between our set push and existing reverse push methods is we push the probability mass from T in a forward fashion by utilizing the symmetry of random walk probabilities on undirected graphs. Moreover, we design a novel randomized push operation, which only samples a small fraction of neighbors to push probability for large degree nodes. Such push operation enables us to avoid the ON term introduced by the original push operation for large degree nodes. To see the details of our set push, a core idea of our method is to utilize the symmetry of random walk probabilities on undirected graphs. To be more specific, for any two nodes S and T in the graph, the random walk probability from S to T equals the random walk probability from T to S, with the multiplication of dt over ds. Such symmetry is very intuitive actually. We can understand this symmetry by considering a specific random walk path from node S to T. The probability of walking from S to T via this path is 1 divided by ds, du, dv, and finally dw. In comparison, the probability of walking from a T to S via this path is 1 divided by dt, dw, then dv, and finally du. We note that the denominators of these two probabilities are nearly the same, except the first one is divided by ds, while the second one is divided by dt. This actually gives the symmetry of random walk probabilities on undirected graphs. By utilizing this symmetry, we estimate pi-t by calculating the random walk probability from the target node T to all the other graph nodes U, instead of the random walk probability from all graph nodes U to the target node T. And for small degree nodes, we adopt the original push method to transfer probability mass in a forward way. On the other hand, for large degree nodes, we only sample a small fraction of neighbors to push probability mass. Specifically, for the large degree node U, we only sample some neighbors from U's adjacency list to touch. Each neighbor is independently sampled with probability RTU over theta times TU, where theta is an error parameter. For those sampled neighbor V, we increase RT by theta. But this means we note that the expected increment is still the same to that of the deterministic push. Above is the high-level idea of our method. We also empirically evaluate the performance of our set push. In our experiments, we used 4 real-world large graphs whose information are listed here. The experimental results show that our set push caused the minimum query time over all existing methods, no matter the target node T is uniformly sampled in the graph or is sampled according to the node degree distribution. In conclusion, in this paper, we consider the problem of estimating a single node PageRank on undirected graphs. We successfully tightened the upper bound for this problem by utilizing the symmetry of random walk probabilities on undirected graphs. A novel randomized push operation is also proposed to avoid touch all neighbors during the push operation from large degree nodes. I would like to use an open problem to end this talk. Since we have successfully tightened the upper bound of the query time complexity as the minimum of dt and the square root of m, a natural question is, have we already achieved the optimal complexity or not? What is the lower bound for this single node PageRank query on undirected graphs? For now, the lower bound is still unclear. That is all of my presentation. Thank you.